Hello, my name is Jonathan Williams. I'm a professor at the University of Hawaii, and I'll be giving a kickoff talk to start the SMA school. So this is a brief primer that introduces everyone to radio astronomy and makes sure we're all on the same page before we get into the details of interferometry and how the SMA works. Now, many of you may well be familiar with astronomy. Maybe you know some of these books. You are welcome to skip this or just crank up the playback speed. But basically, I will just give a very brief 30-minute primer. More details are in these books. The radio window ranges from a little below a millimeter to several tens of meters. The frequency range is from tens of megahertz to about a terahertz. And in this range, the sky is fairly transparent, so we can observe from the ground just as we can in the optical. It's a very large range of wavelengths, 5 decades, and so we split it up into subgroups. The centimeter range is from about a centimeter onwards, the millimeter range from a millimeter to a centimeter, submillimeter below 1 millimeter, and even into the terahertz regime, above 1 terahertz in frequency, about below a wavelength of 0.3 millimeters. The atmosphere is fairly transparent, as I said, in this range, and so especially at a centimeter or more, you can observe from very cloudy places. So radio astronomy was actually pioneered in places like Jersey, Illinois, England, and Holland. And the unifying principle behind the techniques that we're going to talk about is that in the radio regime, radiation behaves more like waves than photons. So we collect the radiation by amplifying how the electric currents that it induces in antennae, rather than looking at, say, the photoelectric effect or a photon kicking the electron out in a semiconductor. The advantage of this is that because we treat it as waves and we measure the electric current, we can measure amplitude and phase. This is critical for carrying out interferometry, as we'll find out. Now, we zoom into the region where the SMA works. It works at a very small range of wavelengths, 0.72 to 1.67 millimeters. And that's zoomed in here, right around a millimeter. And in this schematic picture up here, it looks like the atmosphere is completely opaque, 100% opaque. In fact, down here, you can see that now we're putting transmission instead of opacity. You can see that actually there are spaces where the atmosphere transmits maybe 80 or 90%. And so you actually can observe astronomical signals from the ground at around 230 gigahertz. This is the window where the SMA works most frequently, and also at 345 gigahertz. These are the workhorse bands of the SMA. Now, you can also see there are regions where the transmission goes to zero, or the atmosphere becomes fully opaque. This is generally due to water lines or oxygen lines and other trace species that produce a sort of variable transmission, both in wavelength and also in time. So when there is greater levels of water in the atmosphere, the transmission is lower. So when we observe in these bands with the SMA, we need to understand the transmission of the atmosphere. We need to calibrate that out. So there'll be another talk down the line by Simon Radford, who will discuss in much greater detail the atmospheric absorption and how we calibrate this in our observations. Now, unfortunately, you're not here physically, but you will get a virtual tour of Mauna Kea. And here it is back actually before, just as the SMA was being built. Here are the telescopes on the near the summit of Mauna Kea at 14,500 feet, about 4,000 meters. And that is, 4,000 meters is about 2 scale heights of water. So we're above about a quarter of or more of the water vapor in the atmosphere. So it's a very dry site. And also its close proximity to the equator means that we can do a wide range of astronomical observations. This area down here is known as Submillimeter Valley because it was a pioneering place to carry out submillimeter observations. This is the Caltech Submillimeter Observatory, the James Clerk Maxwell Telescope, and this is the hangar where the antennas were being built, and then it would be populating the region out here. So this is the best site for submillimeter observations in the northern hemisphere. And of course, in the south, we have our down in Treasure. Here's close-ups of those telescopes. The JCMT is a 15-meter single-dish telescope. The CSO is was a 10-meter telescope. It is now has been decommissioned and is actually being removed from the summit as we speak. The submillimeter array is an array of 8 times 6 meter dishes, as you probably are well aware. Okay, so let's move on to what do we see at these wavelengths, and more generally in the full radio range, going from millimeters to meters. Okay, well, at the shortest wavelengths, we see thermal emission that resembles a black body. We call it a gray body because it has an efficiency attached that moderates the black body emission. At the longest wavelengths, we see strong emission from non-thermal sources, synchrotron emission. And then there's also a contribution at all wavelengths from Bremstrom emission. And I'll discuss these individually in the next few slides. But basically, there's strong emission at long wavelengths from non-thermal processes, strong emission at short wavelengths from thermal processes. And the millimeter regime actually around here is near the minimum of these. So the emission is weak, but it's useful because it can be optically thin, and so you can do a lot of saves from that. Let's talk about synchrotron radiation. So this is created by very fast-moving electrons spiraling around a magnetic field. And we know that accelerating charges produce radiation. And so in this case, this is, the radiation is produced traces these fast-moving electrons. If they are spiraling very rapidly, relativistically around magnetic field lines, then the radiation is non-thermal, and the radiation will polarize due to the magnetic fields of preferential direction imposes on the radiation. The distribution of electron energies affects the spectrum of the radiation that is produced. And so by measuring the SED, the spectral energy distribution, you can infer something about that electron energy distribution. Because of the direction imposed by the geometry, you can learn something about that from the polarization of the light. And finally, because this requires very fast-moving electrons that are generally created in supernovae shocks, it tells you, or AGN, it tells you about these supernovae, which relates to massive stars which have short lifetimes, and therefore it tells you about the star formation rate. So down here, we have a nice image at 6 centimeters of the VLA, Cygnus A, a very famous radio galaxy. There's a bright source at the center. This is the AGN, and it's shooting out jets in both directions that produce these huge radio lobes on the sky. Now, this synchrotron radiation is very strong at meters and more. In fact, because it has this strength, this non-thermal kind of process, which creates a very strong emission at long wavelengths, that was the reason why the first radio telescopes, the pioneers, Jansky and Reber, were able to detect radiation. If thermal radiation itself would have been far too weak for these telescopes to detect. And in fact, the strength is very useful because we use these sources as calibrators for the SMA. So here, though, we are using typically in millimeter wavelengths, it is the AGN that we see, not so much the radio lobes, which have a very steep spectrum. The AGN is coming from a accretion onto a black hole, and there's a small range well, there's a range of physical processes, physical radii, that produce a range of radiation over decades. And so it's a fairly flat spectrum, and so bright, relatively bright at millimeter wavelengths. On the other hand, because we're talking about accretion onto a small compact object, there's an intrinsic time variability associated with that. And so these calibrators that we use, these AGNs or quasars that we use, we have to constantly monitor their flux. So this web page lists calibrators as a function of their position on the sky and the frequency of the observations, and also the date. And so you can plot these up to see how that calibrator is varying. This is important to use, and you'll become familiar with this as you start planning your observations. The next radiation processes that I want to talk about also comes from electrons. This is now Bremstrom emission, or braking radiation, as it was discovered in cyclotrons. When they stopped the jets of electrons, it produced a lot of radiation. Again, it's an accelerating charge. In this case, the acceleration comes in a thermal manner. As a plasma as electrons move in a thermal plasma, they move not in a straight line because they're affected by electrostatic forces. And so because their motion changes direction, that's an acceleration and it produces radiation. In this case, because it's a thermal process and it's a chaotic plasma, there is no preferred direction, there is no polarization to the light. On the other hand, the amount of emission that you see at Bremstrom directly relates to the number of encounters between the electrons and the positively charged particles. And so you can get a mass of the ionized gas. And again, also it relates to the density because it again relates to encounters between particles. Finally, because to maintain a plasma in the ISM requires ultraviolet radiation, which comes from massive stars, which have short lifetimes, this gives you a direct handle again on the star formation rate. And here we have a massive star forming region, W49, showing the predominantly Bremstrom gas at 3.6 centimeters with the VLA. Okay, as we move to shorter wavelengths, around 1 millimeter, where the SMA works, then we see dust emission becomes very strong. And this now comes from, not from the gas, it comes from the solid particles, the dust particles in the gas. It comes, fundamentally, it comes from electrons moving in those solid particles. The emission is like a black body, but because the solid particles have a specific size, they cannot emit very long wavelengths, or they emit inefficiently. And so it is a modified black body, a gray body. For ISM grains, they're typically submicron to a micron in size. In protoplanetary disks, they can grow up to millimeters in size. And this changes the spectral index, or the efficiency with which the object emits. So by measuring the spectral index, we can therefore infer something about the grain properties. Now, the emission is also, the amount of emission that you get depends on the amount of dust you have, but because we're talking about thermal emission, as in the black body, it also depends on the temperature. And finally, it can be polarized because the dust grains are not necessarily spherical. And if they are preferentially aligned, then you can get a preferential direction of emission. Alternatively, if you scatter off them, again, you can get a preferential, that induces a geometry on the system, which will again lead to polarization. Here's an example of that. So we have an emitting source here. If this light was unpolarized and its electric field is in every direction, but if it scatters off a source, then the scattering will attenuate the electric field perpendicular to that scattering surface, that scattering plane. And so the light then will be preferentially polarized perpendicular to the scattering plane. And if you were to then observe the scattering from this source, then the angles of scattering would produce a circle around the source. So it scatters off this way, and so on and so forth. So this would be the characteristic polarization pattern that you get from the scattering. You can also have polarization due to absorption or emission from asymmetric particles that are aligned. And the alignment may typically be by a magnetic field. And so again, here's your unpolarized source. As the absorption is preferentially in the long direction of the dust grain, and so what comes out, what would come out in the absorbed light, the absorbed light would be polarized with the polarization perpendicular to the long grain. In this case, we should then relate actually to the magnetic field direction. Your polarization pattern would then look like this. On the other hand, that's an absorption. On the other hand, in emission, the emission would have a polarized, it would have the electric field preferentially aligned along the long axis of the dust grains. And if they are aligned by energy conservation, they tend to be aligned with greatest angular momentum, and therefore in an oblate sense around the magnetic field. In this case, then, your emission polarization vectors are perpendicular to the magnetic field. Now, you'd see emission typically in the millimeter, and you see absorption in the optical. But need not always be like that. We can have scattering in the millimeter and absorption in the millimeter for extremely dense, dusty regions. These figures come from a book, a little bit of shameless self-promotion, from a book that I just wrote called Introduction to Interstellar Medium, which you may find interesting for those who are beginning students. Here is an example of the SMA observing polarized dust emission. The colors in the background here show the total intensity of the emission, and the red lines show the direction of the polarization. And you can see the polarization runs along this way, but there is a curvature to it that you can see on both sides of the source. Now, this is emission, so the polarization vectors are perpendicular to the magnetic field direction. So the inferred magnetic field then has a direction that looks like this on the right-hand side. And you can see that the picture that we get from this is of a collapsing core that is dragging in the magnetic field lines and squeezing them in. The magnetic field lines are squeezed in due to the gravitational collapse. And we can actually see that happen. So the SMA has capability and continues to carry out polarization observations to measure magnetic field strengths, among other things. Shifting gears now to very high redshift sources. At 1 millimeter wavelength, there's also another important aspect that comes when we look at the SED of an object. And I'm going to freeze it right here to show that this is a animation showing the flux versus wavelength, the FTD, for a starburst galaxy, kind of similar to the M82 galaxy that I showed before, where we have, but now the wavelength is increasing this way. So this is synchrotron. There's optical and mid-infrared light here, and this is the big dust thermal emission with a very steep fall off due to the inefficient emission from small dust grains. Now, and I've drawn lines here at 1 millimeter, and you can see that at 1 millimeter, the flux from this galaxy at Z of 0.85 is about 1 millijansky. Now, as I move to higher redshifts, then you'll see that the SED will go down. Let's try again. As we move to higher redshifts, the SED goes down, the flux goes down just due to the greater distance, but it also shifts rightward to longer wavelengths because of the redshift. And this combination means that at this one given fixed wavelength, we just track along this very steep rise in the thermal emission. And so remarkably, you can see here that the flux at 1 millimeter remains at 1 millijansky as you go out to now 2.9. As you continue to go, it remains the same after 3 or 4, or even about 5 or so. So this is called negative K correction, which comes from the infrared terminology, but it's incredibly strong at 1 millimeter. It's a very strong negative correction, and it results in the fact that starburst galaxies, with a very strong dust emission spectrum, a very steep dust emission spectrum, have a more or less constant flux independent of redshift at 1 millimeter. So it means that SMA observations at 1 millimeter effectively can see across the universe in a redshift independent way. So it allows for unbiased observations, unbiased census of star-forming galaxies. It's a very powerful technique. Okay, moving away from the continuum to spectral lines, then we can see that now that there are many other transitions. In the radio, the most famous line is the 21 centimeter spin flip transition of hydrogen. But in the millimeter, the lines that we typically see are from molecules, and they are rotational lines of asymmetric molecules, where the molecule rotates and the center of mass is different from the center of charge. And so again, effectively, we have a moving charge which creates radiation. In this case, it'll be quantized, so you get spectral line information. By looking at spectral lines, and especially looking at different transitions, you can infer, first of all, composition, but you can also infer excitation, which relates to temperature and densities. From the shift from the rest frequency, you can get a radial velocity through the Doppler effect. And again, there can be polarization, which tells you about the magnetic field strength, because this relates to splitting in the energy distributions. And here's an SMA spectrum of Orion KL, a very molecular rich region. And so the millimeter regime, 300 or so gigahertz, can be extremely line rich. The density of lines that make it in the most rich regions that can make it actually very hard to even see the continuum. There's a nice paper by Brett McGuire in 2018 that shows the status of molecule detections. And you can see it's just been steadily rising since the detection of CO in 1970. It has just been steeply rising at a fairly constant rate, almost 4 a year, as new instruments have come online. Most of the detections of new molecules are in the millimeter regime, and also the centimeter tending to find more massive molecules because they have a lower characteristic rotation frequency. And in the ultraviolet, where you can see things like hydrogen, very light molecules. Okay, how do we detect this radiation then? So here is the SMA with its 6-meter parabolic reflector. So the light comes in, is focused by the secondary through the Cassegrain focus to the receiver in the cabin. This receiver has a feed horn that channels that sky frequency into a mixer where we inject a synthesizer or local oscillator to change the frequency down convert the frequency to a few gigahertz, where we have very low noise amplifiers, cryogenically cooled, that then allow us to then digitize and measure the signal. You're going to hear a lot more about the details of that from future talks in this school. Now, I mentioned at the start that the radiation at radio wavelengths is relatively low energy and behaves much more like a wave than as a particle. And so we detect it through the way in which the waves induce an electric current in a conductor. So here is, and that is basically an antenna. So here is our radiation. It comes in and it induces an oscillating electrical field in your antenna. Now, the way the radiation comes in from the sky into our dish, because we down convert it with a local oscillator, the radiation is sent through a diplexer to allow this mixing. That only allows one polarization to go through. So the SMA receivers only measure one polarization. Now, if we want to measure the full polarization, we therefore use 2 receivers. And yes, each SMA antenna has 2 receivers with the antennas in orthogonal directions. Again, there'll be more details about this. But the idea is that a polarized signal creates an oscillating electric field in both antennas, and the direction and strength of the field in these antennas can be used to measure the degree of polarization and the angle of polarization. Now, what do we actually measure? Okay, here is our schematic with our antenna dish here, and we are looking up at the sky at a certain angle on the sky towards the radiation from this source. The amount of radiation that the amount of power that we end up measuring in our detector will scale with, for a uniform illuminated source, it will scale with the degree, the solid angle on the sky. So if I look at twice the area on the sky, I'll get twice as much power in my detector. If I doubled my collecting area, double the amount of power that I get, because I collect twice as much radiation. And there's also a frequency component too. Again, for a flat spectrum, then if I double the frequency coverage, then again, I will double the amount of power that I would receive from my detector. So the power that we see scales with the area, the bandpass, and the solid angle. Okay, and so we can basically factor those out and basically isolate the actual the properties of the radiation that is specific to the source. In fact, we call this the specific intensity. Okay, so the power is measured in watts, but the specific intensity is the fundamental part of the source. That's what we want to measure. That is fundamental to the source. The other aspects are due to the observing technique and the instrument that you're using. So, what is the specific intensity and how do we measure it? So first of all, when we do radio astronomy, we don't use magnitudes, we use Janskys. So what is a Jansky? Well, let's back up and look at the specific intensity. Remember, it is a power per unit area, per unit angle on the sky, solid angle on the sky, per unit frequency or bandpass. Okay, so this is the specific intensity, or it's a brightness. You can think of it as a brightness of the source. It's independent of the way in which you measure it, in the sense that if you use a different telescope, you should be able to derive the same specific intensity as another telescope. As a brightness, it is independent of the source distance. Okay, so this is what we want to measure because it's fundamental to the source. It's telling us the physical properties of the source. Is a synchrotron radiation? What kind of molecule are we seeing? And so on and so forth. Okay, so that's what we want to measure. In practice, all our instruments have a finite resolution. And so we do integrate the specific intensity over some solid angle. We actually therefore measure the flux density, which we call S mu, which is the integral of the specific intensity over a solid angle. And the units then are watts per meter squared per hertz. And that is Jansky, where it's actually 10 to the 26 Janskys because radio vision is extremely weak. But these are the units, fundamental units of a Jansky. Okay, and this is the observable. And because we are now integrating over an angle on the sky, if we were to observe a finite source smaller than our beam, then if that were to be moved further away, then it contributes less. That angle on the sky is a dilution by area, and so it declines with the inverse square law. So flux density declines with the inverse square law. Specific intensity is independent of the source distance because it is an intensity or a brightness. Okay, now you'll also see that this can also be used, we also talk about specific intensity in terms of a brightness temperature. And this comes from, historically, it comes from the centimeter regime where we would look at radiation in this such long wavelength, we were always in the Rayleigh-Jeans limit. And so if you think of the intensity as a equivalent black body, then in the Rayleigh-Jeans limit, B nu is basically 2 kT over lambda squared. And so we can then define a temperature as T as I over basically lambda squared over 2K or C squared over 2K nu squared. And so this is a temperature, has units of temperature, and it's an equivalent way to talk about the specific intensity. Okay, and it's an exact way of the temperature that you measure, the brightness temperature, is the temperature of a black body in the Rayleigh-Jeans limit. But you can also think of it, if you're not in Rayleigh-Jeans limit, or if the specific intensity is not a black body, you can also think of it as the equivalent that a black body would have to be as bright as the intensity that you measure. Okay, now, so we've gone through the very basics of radio astronomy. Now, why are we here? We want to do interferometry. And the reason is the quest is always to higher resolution. We want to see things in more and more detail. The JCMT was a pioneer. It was great. It's 15 meters across. At 1 millimeter wavelength, it could map molecular clouds at 14 arcseconds resolution, which is terrific. But if you want to look at protoplanetary disks, which is what I do, then you want something bigger because protoplanetary disks are only an arcsecond or so in the sky. So you need a bigger dish. Well, This is the biggest steerable radio telescope, the GBT, Green Bank Telescope. It's the size of a football field, 100 meters, but its shortest operating wavelength is 7 millimeters. And so again, the angular size, lambda over d, is 14 arc seconds. So even though this thing is bigger than the Statue of Liberty, almost as big as the Washington Monument, it's still only able to get a kind of blurry view of the sky. You need a bigger dish. And well, how do we do that? If I wanted to get to sub-arc second resolution at 1 millimeter wavelength, you can do the math and you find you need a millimeter wavelength telescope with an aperture of 200 meters or greater. And that's just beyond what we can build. It has something that rigid and to be moved and to be able to work like that. And so instead of trying to build a single telescope like that, you know the answer is that it's not feasible for a single dish. Instead, we build many dishes and we use the rigidity of the Earth to keep them in a fixed location, and we synthesize the signal. We synthesize a larger dish by combining the signals from the individual antennas. Okay, now we can do this in the radio because, as I mentioned at the beginning, we measure the radiation comes in and we measure it as a wave. We measure the amplitude and the phase. So it makes it very easy to actually, relatively easy to combine them. We also digitize it, so we can record it and do it all in electronics. And the electronic revolution has really allowed these huge advances in interferometry. And it's consequently easier to do than in the optical and the infrared. So that's what the school is going to teach you all about. The interferometry has a long history, of course. It began in the longer wavelengths at centimeters in Cambridge by Martin Ryle, who won the 1974 Nobel. So with that, this lecture ends, and I hope you enjoy the school. I wish you well and successful observations with the SMA.